understanding the brain in all of its complexity is a difficult challenge. One of the holy grails of neuroscience is to build an elegant, yet comprehensive theory describing the general roles of the nervous system. Something similar to what a set of Maxwell equations was to electromagnetism. In this video, we are going to talk about the critical brain hypothesis, a theory which has been getting a lot of attention and experimental evidence in recent years. It states that networks of neurons operate near a point of phase transition in a special, critical state, similar to when water molecules coexist in liquid and gaseous phases. But what does it even mean for the brain to undergo a phase transition? There are surely no melting and boiling, right? And in what way is this critical point, whatever it is, important to neural information processing? All of that and more coming right up. To understand the concept of criticality, let's begin with the notion of phase transitions. And one such transition that is probably very intuitive to you is when liquid turns into gas. Consider a pot of water on a hot stove. At first, when the water is below 100 degrees, the energy provided by the burning stove heats it up, accelerating individual molecules. At 100 degrees, however, something interesting happens. Even though the heat is still being pumped into the water, its temperature stays constant. Instead of accelerating individual water molecules, the energy is now being spent on breaking the bonds between them, which allows the molecules to break free from the lattice and fly away as a gas. Notice that at the boiling point, we have seen a qualitative switch from liquid, which is incompressible, has surface tension, and can dissolve substances, to gas, which is compressible and doesn't really dissolve anything. Even though the individual water molecules stayed the same, the macroscopic properties of the system as a whole changed drastically. What we have just witnessed is known as a phase transition. More generally, a phase transition is observed when a system moves from existing in one well-defined state of organization or phase to another. Phase is usually characterized by an order parameter, a macroscopic property that somehow quantifies the organization of the system. For example, in the case of water, order parameter can be entropy, the degree of disorder, volume, fluidity, or surface tension. The phase transition is driven by changes in control parameter, for example temperature or pressure. Essentially, you can think of the control parameter as an independent variable, something that we can freely vary in an experiment. And the order parameter is a dependent variable, which changes in response to altering the control parameter and quantifies the state of our system. Notice that if you plot the order parameter as a function of control parameter, then in the case of water boiling, you'll see a discontinuity, a sudden jump as we go from liquid to gas, accompanied by the absorbance of latent energy. Such phase transitions are called discontinuous or first-order transitions. These are what you normally see in everyday life. However, we will be more interested in another type, so-called continuous or second-order transitions. As you might have guessed from the name, in this type of transitions, the change in the order parameter is continuous, which means that you can smoothly go from one phase to another. Now, the slope of this curve can be very steep, sure, but it's always continuous. This allows the system to exist in a unique intermediate state, called the critical point, right at the interface, when the boundaries between the two different phases are blurred and new properties emerge. This is what makes the critical point so special, as we'll see further. Water can actually undergo a second-order transition at specific values of temperature and pressure. This is where latent heat disappears, and water can be continuously transformed into gas existing in a special state known as supercritical fluid. But to develop intuition about the properties of critical point, let's focus on a different, much simpler system, where the second order transition feels more natural and which actually has a lot of applications in neuroscience. Meet the Ising model, which was first developed to explain the properties of magnets. The model consists of a large lattice, where each site can be in one of two states, +1 or -1. These sites represent individual particles that the system is made of, characterized by their spins, which you can think about as the sign of magnetic field generated by each particle. When all spins are aligned, tiny magnetic fields of individual particles add up, resulting in the magnetic properties on a macro scale. However, when the spins are pointing in different directions, individual magnetic fields essentially cancel each other out, and the system has no macro-scale magnetization. Physicists have known for a long time that if you heat up a magnet past a certain point, called Curie temperature, it will suddenly lose its magnetic properties, so there must be some sort of phase transition at play. Now, there are two types of interactions that govern the dynamics of the system. First of all, neighboring spins will tend to line up because it is more energetically favorable. We can write the energy of a single pairwise interaction between the two sides as being proportional to the negative product of their spins, where the coefficient of proportionality J is called the coupling constant, and it tells us how strongly the sides are coupled. As you can see, when the spins are of the same signs, the energy of an interaction is negative, while for a pair of opposite spins, the value of energy is positive. To find the energy of one site, all we need to do is to sum the energies of the interactions between its four neighbors. And summing together the energies for all the sites will give us the energy of the entire system. Because it will try to minimize its energy, we can expect all the spins to perfectly line up. So what can prevent this from happening? Notice that so far we haven't included our control parameter, temperature, in any of the equations. In reality, however, flipping of spins is a stochastic process, which is subject to random thermal movement. More formally, the distribution of energy values subject to random fluctuations obeys the Boltzmann distribution, which gets more broad at higher temperatures. But it's not that important to understand phase transitions, so don't worry about it. Essentially, you can think of temperature as this stochastic destabilizing force that will induce fluctuations, jostling the spins around and preventing them from settling down into their most energetically favorable configuration. The higher the temperature, the more disordered the system would be. To quantify this, let's introduce an order parameter. For example, the macroscopic magnetization, which is defined as the average value of spins. When the absolute value of magnetization is big, it means that a large number of spins are aligned and our system will display magnetic properties. Let's play with the temperature and see how macroscopic properties of the system change. At low temperatures, local interactions dominate, and the system exists in this state when a large portion of spins are lined up. In contrast, if you heat it up, the temperature-related fluctuations take over. All the spins are oriented randomly, and no macroscopic magnetic properties are observed. Notice that as we turn the temperature knob, there is something that looks like a very abrupt change in the organization of spins, from order to disorder. Indeed, it turns out that Ising model undergoes a continuous second-order phase transition. In other words, it is possible to catch the system in an intermediate state, right at the point of critical temperature where order and disorder are perfectly matched and a number of interesting properties emerge. Before we move to the brain, let's spend a little more time exploring the Ising model. Similarly to how neurons communicate with each other across the entire brain, there is a crosstalk between spins in our lattice. Notice that if you flip one spin, this can make some of the neighboring spins to flip, which in turn affects spins two sides away and so forth. So eventually, even though only nearest neighbor interactions are explicitly defined, the information about flipping one spin has the potential to be transmitted across the entire lattice. In other words, long-range communication emerges from purely local interactions. A good way to measure this is through a quantity called correlation length. For example, let's take two lattice sites some distance apart and look at their dynamic correlation, which is a measure of how coordinated in time their behavior is. More formally, for sites I and j, we can express the dynamic correlation as follows, where angular brackets indicate averaging over time. The first term in the parenthesis represents the amount by which the spin I fluctuates from its average value, and likewise for fluctuations of the spin j. Notice that in order to maximize the value of dynamic correlation, the spins should fluctuate in a coordinated fashion for the product of the parentheses to remain positive. Let's see what happens to the value of dynamic correlation for a given pair as we change the control parameter. At low temperatures, the spins don't fluctuate much, so they are stuck at their average values, yielding a low value of dynamic correlation. At high temperatures, the spins fluctuate wildly, but they do so in a random, uncoordinated fashion. At one point in time, the terms in the parentheses might be of the same sign, while on another occasion they might be of different signs. So on average the value of dynamic correlation is low as well. At the critical temperature, however, nearest neighbor interactions are balanced by the thermal stochasticity. There is a coexistence of coordination and fluctuation, resulting in the large value of dynamic correlation, as spins flip up and down in a coordinated way. So far, we've only looked at the dynamic correlation for a single pair of spins, and that of course will depend on the distance between them. Let's now plot the value of c as a function of distance between the spins for different temperatures. Unsurprisingly, it decreases with distance because we've only incorporated local interactions into the model. And what's prominent is that the curve corresponding to the critical temperature decays much more slowly than the two other ones. For example, we might find that it extends up to 20 sites before it falls to near zero. Let's term this distance, at which the dynamic correlation drops to zero, as correlation length. Drawing correlation length as a function of temperature reveals a sharp peak at the critical point. Right there at the intersection of order and disorder is where large distance communication emerges. If we were to make an analogy, this is the state in which neurons in networks communicate most effectively through the largest number of synapses between them. Another important property that emerges at the critical point is that our system becomes scale-free. To illustrate what this means, take a look at these three magnified snapshots of the Ising model at three different temperatures: exactly critical, slightly below, and slightly above the critical temperature. Can you guess which is which? Well, this is not so obvious because they all look kind of similar. But let's zoom out to see the whole lattice. As we move further and further away, it becomes apparent that the leftmost snapshot corresponds to a subcritical temperature because everything is ordered. Zooming out on the rightmost snapshot reveals a great deal of disorder, so this must be the supercritical state. Now, watch what happens as we zoom out when the system is at the edge of the phase transition. No matter how close or how far away we are, things look very similar. In the ideal case, right at the critical point, this pattern will continue to infinity. In other words, there is no characteristic scale. This self-similarity, when the system as a whole resembles some of its parts at any scale, is a typical property of fractals. Such zooming animations are surely satisfying to look at, but is there any way we can objectively prove that this is scale-free while this is not? To mathematically describe the scaling properties, let's consider the probability distribution of the size of clusters that is, connected domains of the same spin. Here are the examples of a few relatively small clusters and a couple of larger ones. Let's focus on the critical case and build the intuition for what this function f should look like. Suppose a dark wizard has shrunken you to a random size so that you have no idea how tall you are and trapped you in the Ising model at the critical temperature. The only way for you to get out is to correctly guess the probability distribution of cluster sizes. So you grab a ruler and start walking around, measuring the size of every cluster you see. Let's say on average you find out that every 100th cluster you encounter has the size of 4 square inches. So you can write down f of 4 equals 1 over 100. Because the ruler has been shrunken with you, the exact units are irrelevant. What would matter in this case are ratios. So you begin looking for clusters that are 2 times as large, and discover that the probability of observing an 8 square inches cluster is about 1 over 500, which is 5 times as large compared to the probability of seeing a 4 square inches one. After repeating the measurements for a few other cluster sizes, you discover an interesting pattern. Every time you double the size of a cluster, its probability decreases by a factor of 5. Now, here is the crucial point. Let's imagine that you were shrunken to a completely different size. For example, what if you were actually 10 times taller? What would you see in this case? Well, remember, because the system is right at the critical point, it is scale invariant. In other words, no matter how small or big you were, you would see similar pictures everywhere, and hence similar cluster distributions at any scale. So this ratio of the probability for observing the cluster of size 2x versus the cluster of size x would equal to 1/5 at every scale, which means it doesn't depend on x. Of course, there is nothing special about the factor of 2. We could have just as well looked at any other ratio of cluster sizes. So let's substitute the number 2 with a factor k. The value of this ratio will be also different for different factors, because, for instance, the probability of observing a cluster with the size 3x will be different than the probability of seeing a cluster of size 2x. In general, we can write down the right-hand side to be some function j of k, since, as we have already established, it surely doesn't depend on x. This right there is the mathematical definition of scale invariance. So whatever the distribution of cluster sizes is, it should satisfy this constraint. It turns out that the only function for which this equation holds is of the form a times x to the power of minus gamma, where the number gamma is called the exponent. In that case, j of k is equal to k to the power of minus gamma. Plugging in our values for cluster sizes reveals that gamma equals 2.32. This behavior is called a power law, and it is central for the study of critical phenomena. You can easily see for yourself that x to the power of minus gamma is indeed scale-free. Proving it the other way around, that any scale-free function should have this form, is a bit more tricky and requires taking a few derivatives. I won't go through the derivation in this video, but if you're interested, check out the references in the description. Another way to see why power laws are scale-free is to plot a power law function, for example x to the power of minus 2.3, next to something similar, but which is not power law, for example an exponential function. Notice that if we look at the graphs at different scales, the shape of the power law curve stays the same. The only thing that changes are the exact units. If axis labels were erased, we couldn't distinguish them from each other. However, the exponential curve looks different at different scales, and hence is not scale-free. Usually, such relations are plotted in double logarithmic coordinates, known as log-log plots, where you take the logarithm of both sides. In log-log coordinates, power laws look like straight lines, and the slope of that line is related to the exponent value gamma. Importantly, many other characteristics of the system, For example, the value of dynamic correlation we discussed earlier all follow a power law distribution near a critical point. In fact, when you see that a lot of things are power law distributed, it often suggests that the system is near a point of a second-order phase transition. Now, after we've developed an intuition for many important concepts in criticality, let's finally move to the brain. One of the first pieces of experimental observations suggesting that the brain might be operating near a critical point came in 2003 when John Bax and Dietmar Plans published their seminal paper titled Neuronal Avalanches in Neocortical Circuits. They grew cultures of neurons taken from rat somatosensory cortex and put them on an 8x8 grid of electrodes to record spontaneous activity that arises in this network. And what they found was a characteristic pattern of activity spreading across the network in space and time. Let's take a closer look at the data collected by a single electrode. It records how extracellular voltage, known as local field potential, changes with time. If you've seen my video on theta rhythms, it is essentially the same thing. What is usually observed in these cultures of neurons in a dish, however, is that baseline LFP occasionally shows large deflections following a characteristic shape of a negative spike superimposed on a positive envelope. This arises when a number of neurons in the vicinity of electrode activate simultaneously. We are going to treat such waveforms as discrete events that are either present or absent, simply by finding when the voltage trace dips below a certain threshold, and also keep track of the amplitude of every such event. Thus, our data will contain both a time point and an amplitude value for every LFP event that crossed the threshold. Repeating this procedure for all the electrodes gives us the pattern of spontaneous electrical activity spreading in the network. Notice how periods of quiescence are interspersed by what looks like chains of activity arising, reverberating in the network, and finally dying out. Such bouts of activity were termed neuronal avalanches because they resemble cascades of activity propagating in systems like piles of sand or earthquakes. To define an avalanche more formally, let's break up the entire time course into short bins, and for each bin, count the number of electrodes that recorded the LFP event. For example, it might go like this. First, there is no activity. Then one electrode detects the suprathreshold event. In the next time bin, another electrode. Then two simultaneously, then another one, then three others at the same time, and then activity dies out. This sequence of time bins, with some non-zero activity, flanked by at least one time bin of quiescence at either side, is what we are going to call an avalanche. And we can describe each avalanche by its duration as well as its size, defined as the number of electrodes that were activated during the cascade. Note that in the alternative definition, size can also take into account the amplitude values. Surprisingly, the authors found that all these features of neuronal avalanches were distributed according to a power law, revealing a prominent straight line in log-log plots. This suggested that the network activity had no characteristic scale, and that the brain might be operating near a point of a second-order phase transition. Now, all of this happened in 2003, and since then, power law described avalanches of activity were demonstrated in awake, behaving animals of many species, including worms, zebrafish, monkeys, and humans, and on a variety of scales, from single neuron recordings to electroencephalography, suggesting that criticality can indeed be a universal phenomenon which describes many aspects in neural systems. At this point in the video, I think a couple of pieces are still missing. First of all, I've said that the critical point is the intermediate stage of phase transition. But what are the distinct phases for the case of the brain? What would be neural analogs to temperature as the control parameter and magnetization as the order parameter? And secondly, why operating near a critical point would be useful to the brain at all. To make the following discussion more intuitive, let's switch from thinking about avalanches in terms of LFP events on the electrode grid and view the data as activity of individual neurons that either fire an action potential or not. Such switch is justified because of scale invariance. Remember, we are going to see similar behavior at any scale. Plus, it has been established experimentally that there are indeed such spike avalanches, whose features are power law distributed. In this representation, each circle is an individual neuron rather than a single electrode. Now it becomes easier to interpret the activity propagation in the network. Whenever a neuron reaches its threshold voltage, it sends a signal to its downstream partners, increasing or decreasing their probability of subsequent firing. But because neurons connect to each other in very intricate ways, unlike the Ising model, for example, it is hard to see who is connected to whom. Let's make a slight simplification to this network and rearrange the neurons into a layered structure so that information will always flow from left to right. Even though we don't allow any feedback connections or loops, to a first approximation it is a reasonable assumption. And importantly, this description, known as branching model, still allows for avalanches and other critical phenomena to emerge. In the branching model, each neuron is randomly connected to some neurons in the downstream layer, and each connection has a transmission probability associated with it. Upon the spike of a sender neuron, the connection will transmit a spike with a certain probability, and if this happens, on the next time point, the receiver neuron will activate and send the information further. Additionally, each neuron has a very small probability of spontaneously activating even when it doesn't receive any input. This stochasticity provides the network with some input drive to work with. As you may have guessed, how activity spreads in the network will be mostly controlled by the distribution of transmission probabilities. To tune this with a single parameter, let's introduce a number sigma, called a branching ratio, and set the sum of outgoing transmission probabilities for each neuron to be equal to sigma. For example, if the branching ratio is 1, this configuration of outgoing connections is valid because the sum of probabilities is equal to 1, and this is not. By the way, the branching ratio doesn't really tell us the exact number of connections. For sigma equal to 1, a neuron can have 100 connections, each with a probability of 1/100th, or one connection with a probability of 1. The only thing that is constrained is the overall sum of transmission probabilities. It turns out that this branching ratio is a control parameter for our system, and that a phase transition occurs when sigma is equal to 1. To understand why this is the case, notice, from the very definition of sigma, it follows that it is actually equal to the average number of descendants that are activated per single active ancestor neuron. Let's run the simulation for different values of branching ratio and see what happens. As you can see, when sigma is equal to 0.5, any activity that arises quickly dies out. This is because, on average, it takes 2 upstream neurons to fire in order to activate a single downstream neuron. In a real brain, that would correspond to deep comatose state with very little activity. Increasing the value of sigma to 2 causes the network to blow up with activity, similar to what you would see during epilepsy. This is because, on average, single neuron activates 2 others, which makes the activity amplify with time. Something interesting happens when sigma is equal to 1, however. In this configuration, one neuron on average activates one downstream descendant, allowing the network activity to be maintained on a relatively constant level, without decaying or amplifying. Now, because this is a stochastic process, avalanches will eventually die out, but their sizes and durations will be power law distributed. This is why the branching ratio is a control parameter governing the transition from decaying to amplifying activity. And we can use the average density of active neurons as the order parameter, which is really low for subcritical values of branching ratio, but quickly grows as soon as we hit the critical point. By the way, in real neurons, this control parameter, which is equal to the average number of neurons activated by a single upstream neuron, is shaped by the balance between excitation and inhibition, which are the two counteracting forces in the brain dynamics. Importantly, because this balance of excitation and inhibition is something that we can control experimentally, it can further illustrate that there is indeed a phase transition at play. Namely, adding compounds that block inhibitory transmission disrupted the power law distribution of avalanches seen in the normal condition, leading to supercritical behavior. Likewise, adding compounds that block excitatory synaptic transmission leads to subcritical dynamics, again with the disruption of power laws. Okay, by now the only question left is why would brain even evolve to operate near a critical point? Is it actually useful? It turns out that at the critical point, a lot of brain's capabilities, such as information processing and computational power, are maximized. To begin understanding why this is the case, let's think of information transmission as a guessing game. Suppose someone provides an input to the first layer of our branching model by activating a random set of neurons. And our job is to correctly guess the number of neurons that were activated by observing only the output, the activity of the rightmost layer. For low values of branching ratio, no matter how many neurons were activated in the beginning, the activity quickly vanishes before reaching the output layer. We are completely ignorant about the input because there is no activity trace left. For high values of sigma, activity will be amplified, causing the output layer to be fully activated even for the weakest input, which makes the guessing again very difficult. At the critical case, when sigma is equal to 1, the connection strengths are tuned to the optimal intermediate value. Because one neuron on average activates only one descendant, activity of the output layer has a high probability of resembling the activity of the input layer in terms of the number of active units. In other words, observing the output successfully reduces our uncertainty about the input. If we introduce some measure of information transmission that will tell us how accurately we can make this guess, this quantity will have a sharp peak when the branching ratio is 1. Similar to how dynamic correlation peaks at the critical temperature in the Ising model. This, on a very simplified level, is what it means to optimize information transfer. Of course, we have really just scratched the surface of the topic of critical point and its relevance to neuroscience. I didn't really talk about the concept of universality and the beautiful relationship between the exponents, the idea of quasi-criticality, and how the brain actually maintains this right balance in the first place. But if you are interested to know more about criticality and phase transitions in the neuroscience context, I really encourage you to check out a wonderful book published in 2022 titled The Cortex and the Critical Point by John Beggs, who is one of the pioneers of this field. The book is written in a really accessible language and introduces all the concepts from the ground up. Before we move to the summary, I have one important message. In this video, we have seen a few examples of how analyzing neural data can help us better understand the brain. But have you ever wondered how computers can be programmed to process and analyze such complex datasets? If you're interested in the fascinating world of computer science, you're definitely going to love our today's sponsor, Brilliant.org. Brilliant is an innovative educational platform that takes a hands-on approach to learning. Whether you are a student or a professional, it is the best way to learn and excel in STEM fields. Brilliant's courses are designed to be engaging and interactive, packed with stunning demonstrations and exercises. to help you gain intuition and develop problem-solving skills in the context of real-world applications. Brilliant has thousands of lessons for everyone, from foundational math and logic to AI and quantum mechanics, with new ones being added monthly. If you are interested in getting started with computational neuroscience, take a look at the course on algorithm fundamentals, introducing essential array algorithms such as sorting and binary search that underlie the majority of modern computing. And from there, you can move on to programming with Python, which is what I've actually used to run simulations you've seen in this video. Don't hesitate to start your learning journey today. Go to brilliant.org/Artem to get a 30-day free trial of everything Brilliant has to offer. Additionally, the first 200 people to use this link will get 20% off the premium subscription. Alright, let's recap. In this video, we have explored the properties that arise when the system undergoes a second-order phase transition. Namely, it becomes scale-free and there is an emergence of long-distance communication between the components. In the brain, such phase transition is governed by the fine balance between excitation and inhibition, and by hovering near a critical point, our brains optimize information processing. Of course, this area is still very new, so there is a lot of things we don't know. But it is now apparent that the applications of criticality research are far-reaching and exciting, from understanding the general principles of brain function to developing new treatments and therapies for neurological disorders. As our understanding of criticality in neural networks continues to grow, it is sure to be an exciting field of exploration and discovery in the years to come. If you liked the video, share it with your friends and colleagues, subscribe to the channel if you haven't already, press the like button, and consider supporting me on Patreon. Stay tuned for more interesting topics coming up. Goodbye, and thank you for the interest in the brain.